same as the one here, is the same as the one here, right? We have a rate of reaction that can occur in tank 1, some volume 1, then we have the rate that can occur in tank 2, and some other volume V2. And in between we have the concentration of A at 1, that just means leaving tank 1. Okay, that's usually how we write it in this class. 0 is going into the first unit, 1's coming out of the first unit, 2's coming out of the second unit. Alright, and then you have X1 and X2, meaning the conversions after the first unit and the final conversion. Okay, so reactor 1. I'll put a 1 there to indicate that this is the rate constant for the reaction in the first tank. All right, the tanks could be doing 2 different reactions, right? And then reactor 2. So we'll start with the mole balance for reactor 2. Put in the rate law, right? Because we said let's assume they're both first order. So if it's the same reactants, why do I need to worry about putting 2 different rate constants? K1 and K2. If I have the same reactants, presumably the same reaction, right? So what could be different?
Because R depends on the volume.
Depending on volume, no. Rates depend on volume. I was asking about rate constants.
It's dependent on concentration.
The concentrations are different, but are rate constants depend on concentration? No, so somebody said it. Yeah, temperature, right? That might be one reason why I'm operating these things in 2 different tanks. 1, it's more efficient, but 2, I might have this at 1 temperature and this one at another. Okay? So even if the reaction's the same, even if the rate laws are the same, you're still going to have different rate constants for different tanks. Just like I could have different temperature, I might have different co-catalysts, right? I could have catalysts in here. I could have different pHs, whatever. There's so many things that aren't in our formulas that all show up in the rate constant. Okay. And so now if we put that in terms of concentrations. Yeah.
Do you ever take into account the pipe in the middle? Would that be like a...
Like you're worried reaction's going to occur there? I mean, if it was hot, then you might, but a lot of times the transfer pipes aren't kept at reactor temperatures, right? But if it was at the same temperature, you could include that volume somewhere. It would act as a PFR, right?
Yeah.
Yeah. Now, if it was a catalyst, you wouldn't really worry about it, because you'd have something here that prevents any of your solid catalyst from getting out. Even if the solid catalyst is floating around, a lot of times it looks like sandy water, like it's kind of powdery. Like it's a slurry, I mean to say. But you'll have something here to make sure your catalyst doesn't leave, because that's the whole point, is you want it to stay. So you wouldn't have any reaction occurring in the pipe. Okay, so in terms of concentration, that's just factoring out the V naught and recognizing that concentration I can write in terms of the flow rates. So again, I can write it either way. I can write the residence time times the rate constant in terms of the changes in concentrations, or I can write the outlet concentration leaving tank 2 in terms of the inlet concentration, and again, the residence time inside of the second tank. And I already have CA1, so in order to write out CA2 as a function of the actual inlet to the unit, to the pair of units, I just substitute in. So you get CA2, CA naught, divided by 1 plus tau 1 K1, 1 plus tau 2 K2. Okay?
So in practical situations of this, usually isn't it that like they already have a tank and they're trying to build like a second, or they already have a reactor and they're building a second reactor?
That absolutely is often the case. Yeah, it's cheaper. So you guys didn't hear, it's cheaper a lot of times to use a tank you have and build another small tank, right? If I need a little bit more volume, a lot of times it's cheaper to build another small tank instead of just building one big tank when you already got a big tank, a almost big enough tank. So a lot of times that is a reason why you might have two CSTRs in series. You wouldn't necessarily have it when designing a unit, when designing a reactor, a plant from startup, but a lot of times it's retrofitting. Okay, so now imagine in CSTRs in series with identical volumes. Okay? So if they have identical volumes, what's the same in this equation up here?
Tau.
Tau, residence time, right? Residence time for reactor 1 is the same as reactor 2, and we'll just put reactor in. Or we'll just leave it, sorry, just put tau. And let's also assume that the conditions are the same. So if the conditions are the same, then K1 right? Again, that's conditions like catalyst concentration or pH of the system if it's aqueous phase or the temperature. So I can write then the concentration at leaving any tank in would be equal to what? The concentration coming in, that doesn't change when I have this series of n. What does this turn into?
What's tau to the power n?
Right. 1 plus tau times the rate constant to the power of n. All right? And I can also write in terms of conversion. X for some value of n is equal to 1 minus 1 over one plus tau times k to the power of n. So that's CSTRs in series. Let's look at now in parallel. And again, we're going to say same size. Okay? Same temperature, catalyst, pH, etc. Right? So again, now it's a little, you can skip down a little bit. But the taus are all the same, right? Because they're the same size. The rate constants are all the same. So what is it now for all the conversions are going to be the same. Does that make sense? If they're in parallel, then why would the conversions be any different?
They all the same inlet,
Right, they all have the same concentration in their inlet, so they all have the same conversion. It's that simple. Alright, so let's look at an example from the book. This is 4.2, but that's in the 4th edition. So it's probably 5.2 in this edition, I think. They added a chapter, or they split. I should say they split a chapter.
If it's the same feed, the same size, and the same conditions, wouldn't it just be 2 times whatever
Yeah.
one produces?
Yeah.
Okay.
Well, no, the conversions are the same. The flux is twice that.
Yeah.
Right.
Okay.
The conversions are the same.
Yeah.
Yeah, you don't get twice the conversion, right? Everybody get that? How would you, right? They don't know about each other. They're operating independently. Okay, so same reaction that we just looked at, actually. So ethylene glycol from ethylene oxide. So ethylene glycol, or ethylene oxide is this, CH2, CH2, with an oxygen right there, plus water, and sulfuric acid makes ethylene glycol. All right, let's say we want $200 million per year of ethylene glycol, and our feed concentration is 1 pound mole per foot cubed of ethylene oxide with an equal volumetric flow rate of water. This is the type of problem you should expect to see on the homeworks or possibly an exam. Right? You're going to be given a desired goal, and you're going to be asked to design a CSTR that can give you that flux. Okay? So yeah, part A is fine. What's FC?
This is your ethylene glycol.
This is A plus B goes to C. So what's species C? Yeah, product called ethylene glycol. How much do I want? Right, that's in the problem statement. 2 times 10 to the 8th pound per year. Of course, I can convert that into moles because you guys know how to calculate the molecular weight of ethylene glycol. Temperature is constant. K is 0.311 inverse minutes. Do I need to tell you the temperature? Why not?
It's constant.
Because it's constant. Does
Yeah,
that,
it's
does that mean it doesn't matter?
No, it's not that it doesn't matter, but your reaction coefficient.
What's that? It's inside K. What else, though?
It's on the rate.
It's not in the rate law because it's inside K. What if it was a gas? Then would I give you the temperature?
Yeah.
Why?
To calculate the concentration.
To calculate the concentration, you would need it. Right. So the feed here is a little bit weird, right? So what's the problem statement say? 1 pound mole per cubic foot. So I'm given a concentration of a feed of ethylene glycol, 1 pound mole per foot cubed. So it's not a flow rate, but it is a concentration. Okay? And then I'm given, it says that there's another flow. That's an equal volumetric flow rate of water. Okay. So these come together, right? So I have something here. Read what that says. Concentration of one of my feeds, right, at A, but this is just one of my feeds, so you can kind of like, I don't know how you want to do it, but it's not the concentration of the feed. That's after you mix. Okay? Everybody see that? So you guys can come up with your own nomenclature for this, but it's not the concentration of your mixture. That's this. That's your actual feed. So I'm just putting like a little A and a little B to indicate that I've got two streams coming together. Okay, and finally, yeah, you get these concentrations, so you get FAO as well, FBO, and FCO. What's FCO equal to? 0, yeah. That's, if you're not told otherwise, you're not going to lose points for assuming that there's no product. Now, if you're told there's a recycle, that's being told otherwise. All right. So let's start with a little bit of math. Let's put this into, do some unit conversions and bring in the molecular weight. And what you'll get is 6.137 pound moles per minute. So why did I choose minutes?
Okay.
Because my rate constant is in minutes.
Is that 6.137?
Yeah, sorry. I try to make them big, but. All right, so we're going to set aside for a second the tricky inlet. We'll come back to it. So from stoichiometry, so we write out our stoichiometric table. I'm going to write out the whole thing here.
Do we need the density of A?
We need a density. Well, I just said we're going to come back to the inlet.
Oh, so yes.
Let's worry about this other stuff first. FC is equal to what? From your stoichiometric table, what is FC equal to in terms of flow rates? FA naught times conversion. Yeah, that's it. Because remember that the big theta is 0 for species C, because there isn't any in the feed, so that goes away. And then the conversion from the stoichiometry, again, it's A plus B goes to C. So it's just 1 times the conversion. So FA naught now remember, you were given FC. So see, I'm calculating FA naught based on FC. Okay? Again, you're going to get a lot of problems like this, so get familiar with this pattern. If I give you a flow rate that I want, first thing to do, and again, I'll have to tell you the conversion in those situations, is you can calculate the inlet flow rate of A. So now let's look at the design equation. Which was V is equal to FA naught times X divided by negative RA. Right? And then the rate law is what for this one?